Welcome to this explainer, where we're going to demystify the journey of molding raw large language models into robust, scalable production systems. You know that feeling when you build an AI tool and it's an absolute genius in your local sandbox, but the second you push it to live users, it just devolves into a confused mess? Well, if you've been there, you know the pure panic of production AI. Today, we're fixing that. We are taking you step by step from basic prompt engineering all the way up to complex, continuously monitored agent loops.
So, let's just get right into it. Why exactly does a highly intelligent model suffer from what researchers call a cognitive bottleneck? Well, imagine you have a brilliant human assistant, right? And you run up to them and literally shout 15 completely different instructions at once. Summarize this report, extract the themes, rewrite it with a sarcastic tone, translate it to French, and email it to Bob. They'd freeze. They'd drop things. A large language model does the exact same thing. When you throw a massive, all-in-one prompt at it, asking it to execute totally distinct tasks, it's just juggling way too many instructions simultaneously. Because of this cognitive bottleneck, it loses its operational focus, and the errors, they start compounding fast.
The core conflict here is asking a model to do everything in one monolithic prompt versus chaining smaller, focused tasks together. The traditional single prompt approach relies on just one massive API call. Now, sure, it seems simpler on the surface, but it inherently carries a much higher hallucination risk because the model is trying to solve everything, everywhere, all at once. In contrast, prompt chaining is a sequential process. You divide the work into discrete subtasks, and the output of one step becomes the exact input for the next one. This gives the model absolute cognitive focus for each individual step, and honestly, more importantly, it gives you highly granular control over the entire execution path.
Here is our map for the evolutionary arc of your AI systems. We will cover 1. Limits of the single prompt, 2. Power of prompt chaining, 3. Enforcing structured outputs, 4. Decoding the agent loop, and 5. Monitoring AI in production.
Let's start with Section 1, Limits of the Single Prompt, and the subtitle here is The Cognitive Bottleneck.
The illusion that one mega prompt is all you need is something we have to shatter right out of the gate. Centosite research reveals a really fascinating, highly specific metric, 20%. That is the approximate improvement in output quality you get simply by switching from a single monolithic prompt to prompt chaining on complex tasks. When you isolate the model's focus to one objective at a time, it just performs better. It mirrors a professional human workflow perfectly, if you think about it. You wouldn't write, edit, and publish a complex technical report all in one simultaneous brainwave, would you? No way. You'd draft the raw ideas, then review the structure, and then refine the grammar. AI works exactly the same way. Give it room to focus sequentially, and the results improve by a massive 20% margin.
Let's move to Section 2, Power of Prompt Chaining, with the subtitle, Divide and Conquer.
To really see this in action, there's a brilliant study by the UW Interactive Data Lab on AI peer reviews that perfectly illustrates this divide and conquer strategy. They wanted an AI to rewrite raw, harsh feedback to be more constructive. When they tried a single prompt, the AI just gave vague, impersonal advice because it was trying to be friendly and critical at the exact same time. The wires crossed. But then, they broke the task down into 3 discrete sequential steps. Step 1, split points. This just extracted the individual presentation problems from the raw feedback. Step 2, ideate, where the AI brainstormed actionable suggestions for each specific problem it just found. And Step 3, compose points, which synthesized all those problems and suggestions into a final, friendly paragraph. By separating the raw problem-solving from the tone adjustment, the quality literally skyrocketed. Breaking tasks down massively enhances both the transparency of the system and the final output.
That brings us to Section 3, Enforcing Structured Outputs, with the subtitle, The Glue of the Chain. For a sequential assembly line to work seamlessly, the parts have to fit together perfectly, right? If Step 1 of your chain outputs a conversational, messy paragraph, but Step 2 is a script expecting a clean, structured list, well, your entire chain shatters. As developers, we know that a single missing comma or returning a string instead of an integer will crash a production system instantly. That is exactly why we enforce strict schemas. For example, forcing the AI to output exactly a title formatted as a string and pages formatted strictly as an integer. Now, different frameworks handle this structural glue in their own ways. LangChain uses its expression language, LCEL, with abstractions like Pydantic Output Parser to actively catch those type safety errors. On the flip side, tools like Miroscope take a more Pythonic route, relying on native Python and Pydantic, paired with LilyPad for tracing and versioning. Whichever tool you're using, structured output is the critical, non-negotiable glue holding your prompt chain together without failing at runtime.
Welcome to Section 4, Decoding the Agent Loop, with the subtitle Gaining Memory and Autonomy.
Okay, so the crucial point is taking this predictable, structured chain and wrapping it into a continuous, autonomous cycle. This is what Oracle defines as the Level 2 agent. At Level 1 in AI is basically a stateless goldfish. It answers your prompt and immediately forgets you even exist. At Level 2, it loops. The harness begins with Step 1, assemble context, pulling together instructions, retrieved memory, and any previous tool outputs. Step 2, reason. This is where the LLM decides what it actually needs to do next based on that specific context. Step 3, act, where it might call external tools, search the web, or write new memory. And finally, Step 4, repeat. It just cycles through perceiving, reasoning, and acting until a highly specific stop condition is met, like hitting a hard 10 iteration limit or successfully verifying goal completion. That loop transforms our little goldfish into a highly capable, autonomous assistant. But here's the catch. An agent loop without rich memory is just running in circles really fast. To truly elevate our Level 2 agent, we need to inject 6 distinct types of memory to manage its cognitive state. First up is conversational memory, just your basic prior chat history. Next is knowledge-based memory, which stores semantic, vector-indexed facts the agent can look up whenever it wants. Then we have workflow memory, letting the agent recall previously learned action patterns. Toolbox memory allows semantic discovery of tool schemas, so it actually knows what APIs it can successfully use. Entity memory tracks extracted people, places, and organizations over time. And finally, summary memory, which holds a compressed version of older context. Injecting all of these allows the system's harness to actively manage a complex cognitive state, which is infinitely smarter and, let's be real, much cheaper than blindly passing a massive monolithic context window to the LLM over and over again.
Which brings us to Section 5, Monitoring AI in Production, with the subtitle, The Reality Check.
Reaching Level 3 means our agent is highly capable and operating with autonomy. But autonomy in the real world brings massive risk. We have to fundamentally rethink observability. Traditional application performance monitoring, or APM, measures infrastructure health, right? It tells you your CPU utilization is fine, and it gives you a nice 200 OK status code. But in the world of AI, an API can return a perfectly healthy 200 OK status while confidently hallucinating a completely fake product recommendation to your live users. A 200 OK hallucination is a uniquely terrifying AI problem. To fix this, we need dedicated LLM monitoring, like the evaluation layers built by BrainTrust, to measure actual output quality, safety compliance, agent loop depth, and context relevance.
Plus, performance isn't just about total server response time anymore. You've got to track highly specialized latency metrics. Think about the end user, sitting at their keyboard, staring at a blank screen. Time to first token dictates exactly how fast that user sees the response actually start generating. That is absolutely the make or break metric for user experience. Meanwhile, time per output token measures the smoothness of the streaming response once it's begun. If your time to first token lags, your users are going to abandon the session entirely, regardless of how brilliant the AI's eventual answer might have been.
To keep our newly autonomous agent from going completely off the rails in production, BrainTrust highlights the absolute necessity of isolating specific steps with a dedicated judge evaluator. Imagine a travel planning agent that gets confused and just keeps pinging a weather API over and over in an infinite loop. Believe me, it happens all the time. By inserting a judge step, which is a dedicated LLM call that evaluates proposed actions using auto-evals like the exact match heuristic score, the system can successfully validate steps before executing them. The exact match score instantly recognizes the redundant weather check, stops the loop, and saves you from waking up to a massive bill for wasted API calls.
As we look to the absolute bleeding edge of AI engineering, we really have to consider this amazing quote from Oracle. The agent loop and the training loop are converging. The memory layer is where they meet. Pause and just think about the magnitude of that for a second. Right now, we build the agent loop in production, while the foundational model's training loop happens separately, locked away in a research lab. But soon, the high-signal episodic records, those 6 distinct types of memory, and the precise evaluations generated by our monitored Level 3 agents will be fed directly back into the continuous learning pipeline of the model itself. The memory layer literally becomes the bridge between acting today and learning for tomorrow.
Which leaves us with this final provocative thought. If your AI agent is out there autonomously executing tasks, generating its own memory, being heavily monitored for quality, and then using that exact high-quality data to continuously train its own foundational model, when the loop closes, who is really training who? I'm going to leave you to ponder that as we wrap up today's explainer. Thank you so much for joining us on this evolutionary journey from prompt to production. Get out there and keep building smarter.